The goal of this project is to create an acrobot that is capable of throwing a ball to a desired location. An acrobot is an underactuated system, and underactuated systems are interesting because they have the capability to exploit the dynamics, and also they have a more natural motion which is similar to living beings. The two cases shown here are one, a dead fish which can swim through a stream, and the second is a walker without any actuators. Both of these are able to perform the task relying solely on their structure. The problem here has the added complexity that the final state is not known a priori and must be determined during the optimization procedure. Also, there is added complexity that the final state is not an equilibrium, which is unlike the acrobot stand-up where the final state is still an unstable equilibrium. In the problem set up here, the acrobot must first move to gain sufficient energy and then leave the ball at a state such that the ball falls into the bucket. Also, the ball has a velocity of the foot when it is released. This is assuming that the releasing mechanism has no losses. Since the system is underactuated, an optimization procedure is used to find an admissible trajectory that makes the bot go to a desired state. The constraints used in this problem are the system dynamics, the motor constraints which ensure that the solution is feasible on a real system, and the constraints on the final state which ensure that the ball falls into the bucket. After a trajectory is found using trajectory optimization, the real system must be made to follow this trajectory. As a discretized system was used previously, an open loop control law cannot be used here. For this reason, an LQR control law is used which is valid for linear systems. So the system is linearized along the optimal trajectory, and the dynamics of the deviations from the optimal trajectory are linear at every time step. And an infinite horizon LQR controller is used, which has a direct solution and also a function in MATLAB. The control law is also shown on this page, and the derivations are shown in the report. The methodology described earlier is used on a nominal system where the ball weighs approximately 100 grams and the bucket is kept at a reasonable distance from the robot. On this slide, I show the error in the dynamics obtained by discretizing the system. As seen at the naught points, the error is zero, and between the naught points, the error increases wherever the trajectory is fast. The simulation of the acrobot is shown here. It can be seen that the acrobot is indeed able to throw the ball into the bucket. Also, it satisfies the motor constraints and closely follows the trajectory generated by the optimization procedure. Now, the robustness of this algorithm obtained is checked by first weighting the mass of the ball. This simulation is for a ball which weighs 500 grams, and it can be seen that it's still able to throw the ball into the bucket at the same location, and it follows a trajectory which is quite similar to the one obtained earlier. On this slide, the energy consumed by the robot for throwing balls of different masses is plotted in a table. And can be seen that even as the masses increase significantly by a factor of 6 from top to down, the increase in energy consumed by the robot is not very significant for the increase in mass. This shows that the robot is indeed exploiting its dynamics to achieve the desired goal. Now, the time given to the optimization routine to perform the maneuver is changed. On this slide, I show the simulations for 1.5 seconds and for 3 seconds. The simulation for 1.5 seconds is quite similar to the one shown earlier. However, for 3 seconds, it can be seen that the acrobot chooses a significantly different maneuver, which is quite similar to the way someone would throw a ball. The energy consumed by the robot for maneuvers of different time lengths are shown here. It can be seen that for small times it consumes high energy, and also for high times it consumes high energy. So with this table, it's shown that the optimum value of time is approximately between 2.5 seconds and 2.75 seconds. In this experiment, the location of the bucket is varied, and it's seen that with the same algorithm designed earlier, the acrobot is able to throw the ball into the bucket at all three locations. In this simulation, the ball is given a mass of a real basketball and the bucket is exactly the size of a basketball rim. It's seen that here the ball follows a very natural motion, which would be one that is used by humans to throw a basketball. By varying the location, it's seen that the acrobot uses different energies for throwing the ball to different locations. Also, all locations are not achievable because of the limitations on the actuator and the time given to perform the maneuver. It's seen from these experiments that the acrobot has a natural motion which is very similar to the way a human would perform the same task. Also, the methodology developed is robust and the same code can be used to perform all the tasks shown here. And the third thing is that the acrobot is energy efficient as it consumes marginally high energy for a significant increase in mass of the ball. The parameters used in the study are shown on this slide, and all the values were taken such that these can be implemented on a real robot.